Alright, so here's a Fibonacci sequence. We're told the first term is 1 and the second term is 1. And what we can also do is we can say the noughth term is 0. 0 plus 1 is 1, 1 plus 1 would give you 2, and so on. Now, to try and get an explicit formula for the Fibonacci sequence, we're just going to say, let's just try the nth term to be k times x to the power n. And we're going to try and find values of k and x that make it work. It's a bit of a shot in the dark, but let's see where it takes us. So what this means is that top expression there, k times x to the power n, I can just replace it in there. K times x to the power of n minus 1 is going to go there, and k times x to the power of n plus 1 is going to be the lead off. So I'm just rewriting the Fibonacci sequence formula, but in terms of k's and x's. Now if we look at this, every single term has got a k, so we could divide through by k if k is non-zero. And looking at the powers of x, the smallest power of x is this one here, and so if I divide through by x to the power of n minus 1, each and every single term, I'll be left with x squared is equal to x add on 1. Let's gather the terms, recognize that we have a quadratic, and go ahead and use the quadratic formula. That will be b squared minus 4 times a times c, and it's all over 2a. So going ahead and resolving this, I get 1 plus or minus the square root. Looking under that square root, we'll get the value of 5, and it's all over 2. So it looks as though we've got a couple of solutions. Our nth term could be some constant, let's call it k1, times 1 plus the square root of 5 all over 2, all to the power of n. If I just look back to the top line there, I've just replaced x with one of the values. But I could also have done it the other way around. I could have said, oh, let's just give it a second constant, let's call it k2, and chosen the other solution, 1 minus the square root of 5 all over 2, all to the power of n. Now we don't know which one of these formulas is going to work, so what we're going to do is let's just stick them together and maybe add them together. So what I'm going to do is I'm just going to use a big capital A there and do 1 plus the square root of 5 all over 2 all to the power of n, and I'm going to add on a big capital B of 1 minus the square root of 5 all over 2 all to the power of n. So all I've done there is the k1 has become a and the k2 has become b, and if that's a solution and that's a solution, then adding them together should be a solution. I mean, the whole sequence behind the Fibonacci is all adding, so let's just see if this gives us any mileage. Alright, so this is when we go back to our original initial conditions, these ones up at the very top there, and we know that when n is 0, it comes out to be 0, when n is 1, it comes out to be 1. So let's just see where that takes us here. So u0 being equal to 0, if I replace n with 0 in this expression, un is 0, and it'll be a times some bracket to the power of 0, which will just be 1, plus b times some bracket to the power of 0, which will just be 1 as well. So this expression, when I replace n with 0, this expression, when I replace n with 0, simplifies down to that. So in other words, let's just be clear that b is effectively negative a. Okay, now let's look at the other rule which we had, which was the first term was equal to 1. Therefore 1 is equal to a times 1 plus the square root of 5 all over 2 all to the power of 1, plus b times 1 minus the square root of 5 all over 2 all to the power of 1. Now what I can do at this point is I can look at these two terms. The power of 1 isn't going to do much, and I can replace b with negative a. Effectively, I've got simultaneous equations here, and I'm going to go ahead and try and solve them. I've also noticed that, let's just undo that, I could also multiply everything through by 2. So I'd have 2 is equal to a times 1 plus the square root of 5. That b becomes minus a, and I'd have 1 minus the square root of 5. And I've multiplied everything through by 2, obviously. So, multiplying the brackets, I get a plus a root 5 minus a plus a root 5. And what you might notice here is the a and the minus a cancel out, and I've got 2 a root 5 terms. So I'll have 2 is equal to 2 lots of a root 5. Divide both sides by 2, I get 1 is equal to a root 5. divide both sides by root 5, and I get a is 1 over root 5. Now, because of what we noticed earlier, then this must mean that b is minus 1 over root 5. So looking back at this very top statement here, I can now write it out again with a with my chosen value of 1 over root 5 and b with my chosen value of 1 over root 5. And so therefore what I'll be left with is un is equal to 1 over the square root of 5, there's our value for a, times 1 plus the square root of 5 all over 2 to the power of n. And then we put in our value for b. And that bracket was minus the square root of 5 all over 2 all to the power of n. Now you may notice that both these terms have 1 over root 5 common term, so we could just factorize that out, leaving us with 1 plus the square root of 5 all over 2 to the power of n minus 1 minus the square root of 5 all over 2 to the power of n. Now this statement which we have at the bottom would appear to be an explicit formula in terms of n for the nth term of the Fibonacci sequence. We know that it will work for u0 and u1. If I replace n's with 2's, if I replace that with a squared and that with a squared, this should generate the value of 1 because we expected it to. u0 is equal to 0, u1 is equal to 1, u2 will therefore equal 1, you can check that. u3 should equal 2, again if you replace the powers of n with 2. And you could actually just type in this expression to a calculator and see if it does indeed generate the Fibonacci sequence. And truly we have a wondrous moment. We have some expression with powers of n and surds and square roots of 5s, and out of it all comes this lovely sequence of integers. We're done.